So this is a talk on why and how we wrote a Kafka consumer at SignalFX. My name is Rajiv, and I'm an engineer at SignalFX. So the agenda for this talk, we're going to talk about why we wrote a Kafka consumer in the first place. We're going to look at how modern hardware works very abstractly. And then the bulk of the talk is going to be optimizations we were able to do on our Kafka consumer, and we'll see some results at the end. So why did we write a Kafka consumer? So before we get into that, let's talk about what SignalFX does. We're a monitoring platform. We take in high-resolution metrics. We do streaming analytics on it. And we can handle multidimensional metrics. So you could do things like find the 99th percentile of latency by service, by customer, interactively on streaming data. And Kafka is a big part of our infrastructure. We really like that you can combine high throughput with persistence, and so we use it a lot. So the number is not here, but we do in the order of 50, 60 billion messages per day on Kafka. So why did we write a new Kafka consumer? So we actually don't use any of the offset management or partition assignment functionality of Kafka. So really our consumer was meant to replace simple consumer. We do the offset management and partition assignment ourselves. Simple consumer is not a non-blocking consumer, and we wanted one. And since we were writing one, we wanted it to be low overhead. We wanted to be able to consume hundreds of thousands messages per second on a single process. And we're super sensitive to the worst case garbage collection and just worst case latency in general. So we wanted to keep that in mind. And the biggest reason was the Kafka 0.9 consumer wasn't out yet. This talk probably wouldn't have taken place if it was. So what does a Kafka consumer need to do? And everyone here kind of knows this. I'm going to rush through this. So Kafka has multiple brokers. Each broker is uniquely identified by a ID, and the unit of serializability in Kafka is a topic partition. So all messages in a topic partition are ordered. And from the point of view of a client, a single broker is a leader of a specific topic partition. So for a client, the first thing it needs to do is kind of figure out this mapping. So it can send a metadata request and get a response back. It can send it to any random broker, and it forms this map of partition to broker. So let's assume there's a single topic for now, so it's just partition to broker. It needs to figure out what offsets to consume for the partitions it's responsible for. So it could get it from the consumer group or some external source. Once it gets this, it can actually send in a fetch request. It will send in a fetch request to every broker that at least one partition falls on, like any one of the partitions that it's interested in. Then it gets a response back and moves its offset along, and that's really what happens in steady state. So before we talk about optimization, let's talk about how modern hardware works. This is going to be very abstract. But hopefully we'll still get something important from it. So this is a simplistic diagram of a 2-core single-socket modern, say, x64 processor. So a good way to think about modern processing systems is to think of them as distributed systems. So on one end, you have your number-crunching cores. On the other end, you have your memory subsystems supplying it, and they're all connected by a fast network. So in the past couple decades, I would say, the core speeds have gotten a lot faster than the memory subsystem supplying it. So all good distributed systems engineers, processor designers decided to add a bunch of caches because that solves everything. So L1, L2, and L3, these are all caches. And a good rule of thumb is that the closer you get to a core, the faster a cache is. So L1 is faster than L2, which is faster than L3. But the closer you get to a core, the smaller the cache is. So L1 is smaller than L2, which is smaller than L3. So typically, L1 is around 32 kilobytes, so it's really, really tiny. And you'll see L1 is private to a core. It's usually segmented into data and instructions, so that's the D and the I. L2 is still private to a core, but not segmented. L3 is usually shared by all cores in a socket. So how does data move from memory through this cache hierarchy? So let's say that we wanted to move this piece of memory containing the single number 1. Well, memory actually moves in fixed size blocks called cache lines. So on x64, this is usually 64 byte. So if you're trying to move even a single byte, the whole 64 byte aligned cache line is going to come along for the write, so you better make it useful. So let's say we wanted to move this number 1, well, the whole cache line is going to move. Okay, so that seems like a complicated system. So the memory subsystem makes, well, not 2, 3 kinds of bets to really help us. Temporal locality just says that if you've used a piece of data, you're very likely to use it again in the near future. So this is very much like LRU cache kind of principle. Spatial locality says that if you've used a piece of data, you're very likely to use something close to it in memory. So the fact that cache lines are 64 bytes is already an example of spatial locality. And then there's prefetching, which you can probably merge in with spatial locality. Prefetching just says that the processor actually tries really hard to figure out your memory access patterns, and it is going to try to hide this latency by pipelining cache fetches while you're processing data. So anytime you're predictably accessing memory, say you're linearly walking an array, the processor is very good at doing this, and it will just hide the entire latency from you. On the other hand, if you have unpredictable memory access, let's say you're walking through a linked list or traversing a deep object hierarchy or doing a lot of hash map lookups, these are random memory accesses that the processor cannot predict, so you get cache misses. Okay, so let's take an example. So imagine we have an application where you're summing up all the nodes of a linked list, and these nodes contain just numbers. So let's say this application is running on core 1, and our linked list only has 2 numbers, 1 and 2, but they're very far away from each other in memory, so they fall on separate cache lines. So what's the core application going to do? It's going to try to load the memory, which has the number 1 in it. It's not going to find it in any of its caches, so it's going to create an entry in each cache and copy it over. So it goes to L3, then to L2, then L1, and finally it lands on a register on core 1. Then it looks for the memory containing the number 2. Again, it's not in cache, so it loads it in L3, then L2, L1, and finally on a register. And now it can add the 2 numbers. So you can see that we require 2 cache lines, cache misses to really add just a couple numbers. Here's another application running on core 2. This time it's trying to add 8 numbers, and they're in an array, so they're right next to each other in memory. Let's assume that the array starts at a 64-byte alignment, so it's on a cache line. So what happens now? Again, the core tries to load the first element of the array. It's not there. That's a cache miss. Going to copy it all the way up and get it in a register. Now it tries to load the second element, but it's already in cache, so you just get it right there. Same with 3, 4, 5, 6, 7, 8. And now you can add it. So 8 numbers could be added with a single cache miss, whereas we saw previously only 2 numbers could be added with 2 cache misses. So it's actually very possible that you could add 1,000 numbers before you could add 2 numbers, depending on the layout in memory. So here's a chart showing the relative speeds of access. And the absolute numbers don't really matter. They're probably outdated by now, but you can see that main memory can be 200 times slower than L1 cache. So here's a little animation to really drive home the point. So let's assume that you have some data in your L1, and let's assume that this is the amount of time it takes to access it. So that's pretty fast. Now here's the same for L2. Still pretty fast. So I've dedicated around 90% of my talk time for this one slide. So let's look at main memory. That's how fast it is. So all the old advice around not using expensive instructions like divisions or square root are just secondary effects now. This main memory latency is what we're really fighting against, and that's what we kept in mind when we were optimizing our client implementation. All right, let's wait for this. All right, done. All right, so what kind of optimizations did we do? Well, before we talk about that, let's talk about the aims for our optimizations. We are not trying to get more data per second from our consumer. Even a very inefficient implementation will probably be bottlenecked by the network. So what we're trying to do instead is to get out of the way of the application. We already talked about the fact that caches especially are shared resources. So we want the consumer client to use as little of it as possible and leave all of it to the application. And again, just to reiterate, these resources are actually really rare, like 32K of L1 cache, that's like nothing. So we value efficiency versus raw speed. So the ability to do the same amount of work with fewer resources as opposed to doing more work in less time. So what are the resources we care about? Well, fewer cycles means more cycles for the application, less cache usage, fewer cache misses means more of it for the application. We really care about this one. Less memory, it's good to use less memory, but we don't care about it as much. So again, efficiency for the client means more resources for the application, which means more speed for the application. That's what we really care about, more speed for the application, not the client. Okay, so almost all efficiencies actually come from constraints. There's no magic insight that we had which made us go a lot faster. So what are our constraints? Well, we didn't need any consumer group functionality, so our client could be very simple. We had a single topic which could be frozen as soon as the consumer was created. Finite number of integer partitions, this one makes sense. Partition reassignment is rare and happens during startup and shutdown. This is probably true for most Kafka-based applications. This is a really important one. We're in complete control of the code that actually consumes these messages. So there's a lot of chance to apply the end-to-end principle well when writing our client. All right, so the first optimization we did, we talked a lot about caches and how they work. We used very cache-conscious data structures. So here's one example that we're actually going to go into detail. We use arrays and open addressing hash maps whenever possible. So we have a single topic, less than 1,024 partitions. So all partitions implicitly belong to this one topic. So we don't have a concept of topic partitions. So partitions are just simple integers, so we can use arrays instead of maps. When we cannot use the arrays, we actually try to use primitive specialized open addressing hash maps. That's a mouthful, but they work a lot better than Java's hash maps. All right, so how do we convert topic partitions to simple arrays? So let's assume that you have an offset table, which every Kafka consumer kind of needs to keep track of the next offset to consume. Let's say we have a single topic foo and partitions 0 to n, and those are our offsets. So we know that we have a single topic foo. So now our hash map can actually be from an integer partition to an offset instead of being a hash map from this class to, or this object to another object. Now we know that partitions are simple integers from 0 to n, where n is the maximum number of partitions for that topic. So we can actually convert this into a single sparse array with the index of the array being equal to the partition. So the 0th partition's offset is in array 0. So why do we hate hash map so much? So let's assume that we've implemented our partition to offset table using a Java hash map. Java hash map is implemented as an array of references to linked lists, which themselves have references to a key and a value. So lots of indirections, and so you can probably see where the story goes. So let's trace a simple get operation on this hash map. The first thing you do is you hash your key, which is a partition. You land on a random offset, and that's a cache miss because this was completely unpredictable, and no hash map can really avoid this. But this isn't now an entry reference. Entry reference, we kind of need to follow through the actual contents. So that's another cache miss. Remember, references are leading to somewhere completely unpredictable. That's another cache miss. Now we need to check if the partition is actually equal to the one we were searching for. It's a boxed integer, another cache miss. Now we return the reference to the offset. That's not a cache miss because it was in that same cache line that the partition and offset were there together. But when you actually dereference it and try to get the actual offset, that's another cache miss. So Oprah says cache misses for everyone. All right. So we think of a hash map, Java hash map, as a dependable cache miss generator. So no to it. What about a sparse array? So let's imagine that we're trying to get the offset for the fourth partition. Well, you just load the fourth index, so it's a single cache miss. Why is it a cache miss at all? Because again, the processor doesn't really know what you're trying to do, so this is still unpredictable. But it's 4 times less cache misses. All right, so to show that this is actually a trade-off and not a pure win, here's how much space it'll take in memory. So let's assume an extreme case that we have a single partition assigned to us, but our topic can have like 1,024 partitions. So this is how much memory a Java util hash map would take. We're assuming 4-byte references and 8-byte headers, which is probably a little generous, but around 64 bytes. Whereas our sparse array needs to allocate 1,024 longs, that takes around 8 kilobytes. That's a lot more memory. But what about cache though? So each cache miss loads a new cache line. And so we had 4 cache misses there, so we load 4 cache lines. The reference array, the actual contents, the boxed partition, and the boxed offset. So that's 4 cache lines, each 64 bytes, using 256 bytes in cache. Remember, this is the precious resource. We only have 32K of this. What about the sparse array? Well, that is a single cache miss. It loads a bunch of garbage that is not needed, but that's 64 bytes. So something that uses 64 bytes in memory can use 256 bytes in cache, and something that uses 8 kilobytes in memory can use 64 bytes in cache. This is kind of not very intuitive. And I like to think of it a little bit like virtual memory versus physical memory. It's okay to use more virtual memory as long as it helps you limit the amount of physical memory you use. So here, our virtual memory is actually the physical memory, and our physical memory is the cache memory, which is our rare resource. So that was just one example of a cache-conscious data structure. This could be an entire talk, but all our data structures are built with these principles in mind. Our queues are built from simple integer arrays. We use negative to overload the meaning. Zero allocation hash wheel timers. These are built from primitive long arrays. We use open addressing hash maps, also built from primitive arrays. We use bit sets on top of long arrays whenever possible instead of using Java util sets. And there's actually very efficient traversal for this. So you can see the common scheme is kind of, we try to prevent indirection. We try to make it boil down to walking an array, because x86 processors are built for that. All right. So benefits, we think benefits are kind of medium. Java, the Kafka consumer 0.9 actually has a lot of little hash map lookups. Sadly, the sparse array optimization, which we think is awesome, is not very applicable because the consumer 0.9 actually supports multiple topics. So this is not a very generic optimization. On the other hand, we think by switching to open addressing hash maps, which we're not going to talk about at all, you can actually preserve most of the benefits, whereas you avoid most of the loss of flexibility that comes with sparse arrays. All right, the second optimization, create buffers once, reuse. So again, we have a single topic with a finite number of partitions. As soon as you create the consumer, the topic and the client string are immutable. So they can be frozen, and anything that depends on that can be written once and just reused over and over again. So the metadata request can be just created once and reused over and over again. Offset requests and fetch requests have a fixed part that can be written once. The per partition part has to be written again. So let's take an example. Here's a fetch request. Kind of how it looks in memory. This is the Kafka protocol. So there's that fixed size part, and the size of a fetch request buffer actually completely depends on the number of partitions. So as long as the number of partitions assigned to you has not increased since the last, say, poll call, you can actually keep reusing the same buffer. So what we do is when we create one of these request buffers, which is rare, we create an index to it actually. So here what we're saying is that the index says partition 0's offset is at position 1200 within this byte buffer. Partitions 1's is at 1216, partition 2's is at 1232. Now, we remember our sparse offset arrays, so what we can do when we say, let's imagine that this is the fetch request buffer from our previous fetch request. Our offsets have moved on, as you can see in the offset column. So when we need to create a new fetch request buffer, we just look up those offsets and plop them right on the byte buffer. We don't need to allocate a byte buffer. We don't need to copy all that stuff. It's just swizzling a few integers here and there, or longs rather. So the offsets move on, and now we can send this buffer. So this is how the code looks like. We're iterating through a bit set of partitions. The real meat is there. We get the buffer position for offset from this array, again, a simple array. We look up the next offset from another array, and we directly write it to the buffer, and we're ready to move on. So we talked about the metadata request. It's actually doesn't change at all, so you can just keep reusing this. The offset request, again, there's a fixed part and a variable part, which only depends on the number of partitions. So again, we can create an index to just this, and so when we need to create a new offset request, we can walk this index and just write our partitions and send it. So benefits and application to the 0.9 consumer. So we think the benefits are high. Again, reuse instead of allocating means that thing stays in cache. Temporal locality, we touched on that. When creating a new fetch request, this is ridiculously fast. We're just walking through arrays. We're helping, the processor is helping us by prefetching things. One fetch request per fetch response, so this is not some rare use case. This happens pretty often. The metadata and offset requests are probably rare, so probably not too useful. Applicability, we think it's high because it's an internal detail, so we don't need to change the API. And even for consumer groups and all kind of other clients, partition reassignment or partition migration to new brokers just don't happen that often. So we think it's a valid optimization to actually create this array whenever one of these events actually happens. Right. The last of our optimizations, and this is a really big one, this helped us the most, is zero allocation response processing. So what does that mean? So our messages actually have our own handwritten schema. They don't need to be deserialized into some POJO. Just like Kafka's protocol, you can just take the byte buffer, read an int at an offset, a long at another offset, and you can read your message just like that without creating any Java objects. So what we try to do is as soon as we've parsed the message in Kafka's protocol, we can actually pass it to our application. So this can be done without any copy or any allocation at all. And again, given that there's no deserialization required, a copy or allocation is actually very expensive compared to reading some memory which is already in cache. Benefits really add up, again, when you're processing hundreds of thousands of messages per second. So the problem with the solution is the interface is a little low level. Our application implements something called a Kafka message handler. So you pass each message as a byte buffer, and the real message is denoted by this position and length within this byte buffer. So our poll call actually takes one of these handlers and a timeout, and each time it parses a message, it calls the handle message, it waits for the application to return, and then goes on to the next message. So let's imagine that this is a fetch response buffer, and there's a bunch of fixed size stuff again on top, or at least not important stuff. We come to the first message set, we parse the length of the message, we've done the CRC to know that this is a valid message, and so we can just pass this entire byte buffer with this position and the length of the message to the application, and it's sitting right there hot in cache. The application processes it, we move on to the next message, do the same, and the next message. So this looks very much like streaming through an array, and we already talked about how good processors are at doing that. So again, benefits we think are very high. First of all, we use the same response buffers over and over again. So no allocations, there's temporal locality there again. Data is processed right after being read from the socket, again, temporal locality, because it must be in cache, given that you just wrote to it. You're streaming through a buffer. That's, again, spatial locality plus prefetching. So the processor really helps you here. The other nice thing is we can actually use direct byte buffers here instead of the normal thing that most Java code does, which is use heap byte buffers. So the reason people use heap byte buffers is usually because direct byte buffers are very expensive to allocate. Given that we only allocate this once and keep reusing it, direct byte buffers are totally fine. And direct byte buffers, you can actually do a socket read without any copy, whereas if you read into a heap byte buffer, Java will do a copy for you in a thread local direct byte buffer. Well, actually, the read in a thread local direct byte buffer, then copy it over to your heap byte buffer. So again, we're totally zero copy in the Java land at least. There's still a copy in the OS, but we're not trying to really fix that. Applicability, we sadly think it's too low. API is very low level. I've had a hard time pushing my agenda on the Kafka mailing list. Integrity of internal buffers can get compromised because the application can keep a reference to this byte buffer, or it can write stuff there. You just don't know. And the Java type system is not strong enough to prevent any of that. Maybe, just maybe, there's a low level with great power comes great responsibility API or some other solution. I'm not a very good API designer, so I'm not sure what can be done. All right, so some numbers. We did a lot of optimizations, but did any of them actually help? Okay, so sadly, this is going to be a benchmark, not our real application. The benchmark is very similar to our application, and again, I think most applications which would benefit from a consumer written like that, like this, actually shares a lot of characteristics with our application. Each message is processed very cheaply. Probably no copies required to process a message. It can be processed synchronously. So given all of those constraints, this might be useful. Again, there are many, many choices for a client. Ours is not better in any way. It's just super tuned for our workload. It will and definitely will prove bad for other workloads. All right. So what does the benchmark look like? So we have a single topic partition that we're consuming from. So the benchmark either runs our consumer or the 0.9 consumer. The settings, the Kafka consumer settings are exactly the same. There is a producer running on a separate process, which produces 5,000 messages, which is a very low number. Only on that topic partition, each message is 23 bytes. Don't ask me why. All the consumer does is reads the message, takes out a few fields, which is like a couple longs really, and writes them somewhere in memory. We make sure that it is not optimized by the Java JIT. So we warm up for 5 minutes under this workload, and then we profile for 5 minutes. So over a run of 5 minutes, it's around 1.5 million messages. And we use Java Mission Control, which we found to be a very accurate profiler to actually profile this application while it's running. So this is how 0.9 consumer looks in terms of allocations in the thread local allocation buffer. So it does around, I think, 423 megabytes for 1.5 million messages. That's actually really good. You'll see a lot of those allocations are in message parsing and message iteration. So we've talked about a way where you can actually make this go to complete zero. You can see those byte buffer slicing. That's the thing where it's creating new messages. What about our client? Well, we allocate 218 kilobytes for 1.5 million messages. And sadly, the entire 218 kilobyte is from Java select call. Surprise, surprise, Java allocates. We actually plan to use a hack inspired by the Netty project where we can actually get rid of this to go actual complete zero allocation. But we're pretty happy with this. 1.5 million messages with 218 kilobytes is not too bad. What about the code profile? So again, Kafka Consumer 0.9 is actually really, really good. So the entire benchmark took around 6.6% CPU while it was running, and the 0.9 consumer takes around 91% of that, so that's around 6% CPU. This is a really bad machine, by the way. So you can see again, some of it is in the checksum math. The other stuff is in iteration. It's spread all over the place. If you dig in deeper, there's going to be a bunch of hash map lookups here and there. And they really add up, especially for the application, not for the client itself. So overall, it used around 6%. So our application used around, or our consumer running on the benchmark used around 2.63%. out of which 50% was us. So it's around 1.3% CPU, out of which 16.67% is actually, again, that damn select call. So really, we use around 0.8% in our own code to process 5,000 messages per second. So again, we're very happy that we can process 5,000 messages per second with 0.8% CPU. But we're going to count the select call. After all, we're making it. So overall, the numbers stack like this. You'll see that the 0.9 consumer uses around 4.6x CPU. Again, probably no one cares because it is only 6% after all. It allocates a lot more. But again, most people probably don't care. We care because we really, really care about our worst case GC. We try to actually keep it within single-digit milliseconds. So we tried the same benchmark with around 10,000 messages per second, and you'll see that the relative numbers are kind of still similar. It's around 4.2x more CPU taken up and around 2,000 times more allocations done by the 0.9 consumer. So actually, that brings my talk to an abrupt end. And there's my contact. And we're hiring if you're interested in stuff like this. So I'll be happy to take some questions now.
All right. We'll start up at the front, work our way back.
So are you using compressing?
We're not actually, but there is an easy solution. If you're using compression, you need an extra buffer. And so as you get each message set compressed, you just copy the entire or decompress it into one buffer. So you still don't need allocations. And then you iterate on the actual, the second buffer, and then you go back to your first buffer.
Okay.
Rinse it.
So another question is that do you have a multiple thread doing the same thing?
No, we have a single thread doing this.
Okay.
So each thread that, so already our partitions are, we divide our work amongst threads. So one thread is responsible for an entire partition. So wherever we're running this, we make sure that we divide our code based so that there is no broker overlap. So each partition, or if partition 2 and 3 belong to broker 2, we're going to make sure they're processed on the same thread. So we get good batching.
Okay. Then, so I suppose you didn't see any context switch caused the core thrashing, right? Did you?
So for one part of our application, we actually bind our threads to a core using JNI. So we don't see any context switches there. But we haven't measured them. We just assume that Linux works. So yeah.
Who else?
So are you planning to, try to propose, to contribute some of those changes, the ones that are of high applicability to the new consumer?
Yeah, I think so. It is not very applicable as it stands, again, because of the constraints, but I think some of the things definitely are. So we'll try to contribute code. We're actually trying to move to 0.9 consumer, but right now the performance for this is a little too good for us to move. So we're going to try to go the route of trying to propose these changes and see where it lands us.
So for the memory improvement, can you give me some details about like which percentage comes from which optimization you have?
I don't have any answer to that. It's very difficult to measure that because you can't measure, especially for cache, which part of your code is taking how much cache. You can do some simplistic modeling, which is what we've done. The amount of memory we use is very similar to actually how much memory Kafka uses, the 0.9 consumer, which is already pretty low. It's just that our memory is, some part is very cold, but the amount of hot memory we use, which is in cache, is actually very little. So that's, again, the whole point. And we have a bound on that, again, but this is based on math and not measurement. So,
Anyone else? All right. Thanks, Rajiv.
All right, thank you.
All right. Anyone have any general questions about Kafka or from any of the other presentations?